The other equation is, since it's perfectly elastic, I know kinetic energy is conserved, so my total kinetic energy beforehand, 1/2 m1a squared plus 1/2 m2b squared, that's my total kinetic energy beforehand, is equal to 1/2 m1c squared plus 1/2 m2d squared. Dramatic pause for people who ask questions about how I got these two equations, or other questions. All right. I want to get M1s together and M2s together, so I'm going to get M1s on the left-hand side and M2s on the right-hand side for both equations. So I got M1A minus M1C. It's going to be equal to M2D minus M2B. So the first equation, just took my M1C over to the other side and my M2B to the other side. Something very similar here. I am going to do one step beforehand. I'm going to multiply everything by 2 to get rid of those 1/2s. So multiply everything by each term by 2. And so I end up with M1A squared minus M1C squared equals M2D squared minus M2B squared. It almost looks nicer. I'm now going to factor, because my left-hand sides, every term has an M1 in it. My right-hand side, every term has an M2 in it. So if I just factor the masses out, I get M1A minus C equals M2D minus B. And down there, I've got M1A squared minus C squared equals M2D squared minus B squared. I want to factor that second one again. How do you factor A squared minus C squared? How do you factor difference of perfect squares? So I got M1, A plus C, A minus C. So if you FOILed that out, you'd get A squared minus C squared. And that's going to be equal to M2 D minus B, or D plus B, whichever one you want to do first, and then the other one, D minus B, D plus B. So that second equation ultimately comes down to this. And again, the math people claim as long as I divide both sides by equal denominators, it's legitimate. So I'm going to multiply or divide the left side by M1 A minus C. And I'm going to divide the right side by what that's equal to, which is M2 D minus B. Mass 1 cancels out there, mass 2 cancels out there. A minus C cancels out. And on the right-hand side, D minus B cancels out. It boils down to A plus C is equal to D plus B. Traditionally written slightly differently, they get the initials together, so that's A minus B is equal to D minus C. The physical meaning here, I have that 4 kilogram, in that last problem, that 4 kilogram mass going at 10 meters per second, pursuing that 8 kilogram mass going at 1 meter per second. This is from a side view. We're standing on the side watching this pursuit happen. But if you were here, if you were in the 8 kilogram mass, what you would see is that the 4 kilogram mass is approaching you at 9 meters a second. So from the point of view of the 8 kilogram mass, 4 is approaching at 9 meters per second, just the difference. After the collision, we had the 4 here going at, it was going this way at 2 meters per second. And the 8 was going this way at 7 meters per second. Well, from 4's point of view, it looks like 8's going away at 9 meters per second. Again, it's the difference, 7 minus -2. So 10 minus 1 is 9, 7 minus -2 is 9. This is known as the relative speed of approach, the relative speed of recession. Relative speed of approach equals relative speed of recession. If we actually plug that into the previous problem, we had 48 is equal to 4s plus 8t. That's where. And then, so I still have 2 unknowns. So I have 2 equations. So I have, this is one of my equations. And my other equation is, I don't pull out the kinetic energy equation, I pull out that equation. 10 minus 1 is equal to t minus s. There's no quadratic here. You isolate one, so t is equal to 9 plus s. Plug that in for here. If I divide by 4, I get 12 is equal to s plus 2 times 9 plus s. 12 equals s plus 18 plus 2s. -6 is equal to 3s. S is -2, which is what we had before. Questions before I ask my next one? When we solved this before, we had 2 solutions. One was they never collided, and one was they collided. In this method, we lost the they didn't collide solution. We lost that original information in terms of the answer. Where'd it go? At what point in our math here did suddenly the 10 and 1 solution disappear?
Because of that equation that A minus B is equal to D minus C. That didn't give us this.
This one right here?
Yeah.
Yeah, but somewhere before then, that the solution that they hadn't collided yet suddenly became unviable. Because we have -2 here, which means that t is equal to 7. But what happened to s equals 10, t equals 1? That's one thing that the mathematicians haven't figured out how to do yet. Besides the Millennium Prizes. Something which my son's 2nd grade teacher didn't have trouble grasping. A very obscure clue. I divided both sides by equal things, but when can I not divide by equal things? Luis, it looked like you have the answer, but just afraid to say it.
I don't know. When this is 0?
Yeah, you can't divide by 0. Mathematicians haven't figured out how to do that yet. Notice here, when I divided, masses aren't 0. But I got a difference here. I got A minus C. Well, A in our problem here, A was 10. I can do this, I can divide by A minus C as long as C is not 10. D is 1, and I can do this as long as B is not 1. This is the point in which that other solution basically disappeared. So the advantage of this method is you're not dealing with quadratics. But you lose, the disadvantage is you lose that quick check at the end, because if you use the quadratics method, the first method I chose, one of your solutions will be they hadn't collided yet, and so that is a pretty good indication that you are definitely on the right track. Or if you don't get that, then you know you've done something wrong. Questions before I show you a third different way of solving the exact same thing? Now, the third way has the advantage of, personally, I find it the easiest of the 3 methods. It has a disadvantage, is it's slightly more abstract. So we will take a specific case of the problem that we started with. I got a 4 kilogram mass right here, cruising along at 10 meters per second. And I've got the 8 kilogram mass cruising along at 1 meter per second. My momentum is 40. Give myself a little bit more space here. So in the lab frame, we're just standing off to the side watching it. My momentum was 40 plus 8, which is 48. Okay, that should be a rehash of something we've done already. All right, now I want to change point of view. Suppose I am in the 4 kilogram mass. So the 4 kilogram point of view. If I'm in the 4 kilogram mass, according to me, how fast am I going?
10 meters per second. 10 meters per second.
No. Think about you're in a car. How fast, from your point of view, how fast are you going when you're in a car?
Like, that's the person.
Yeah, you're sitting in a car.
Sitting in the car. I'm not moving. The car's moving.
Oh, not,
Do you want us to say like it looks like the ground's moving?
yeah, that's where I'm going. From your point of view, you're not moving at all. Everything else is just zipping past this way, assuming you're going forward. So from the 4 kilograms point of view, this is 0. So my velocity is 0, so 4 times 0 is 0. How fast will it seem like it's going? All right, first off, I'm sitting right here. Based upon your observation, I'm going 10 meters per second. From my point of view, I'm not moving at all.
Does it look like it's going backwards?
Yep, how fast?
9 meters per second.
Yeah, so it'd be -9, and so my momentum would be -72. So -72 Descartes. So from the 4 kilogram point of view, my total momentum of the system is -72 Descartes. Notice when I went from here to here, from the lab frame to here, I subtracted 10. I do the same thing here, I subtracted 10. From the 8 kilogram point of view, how fast is the 8 kilogram mass going?
0.
How fast is the 4 kilogram mass going? so those are V's. So my momentums would be 9 times 4, which is 36. That's 0. And so I have 36 Descartes. So my total momentum really depends upon the viewpoint. You got the lab frame or the problem, what you're reading on the piece of paper. You have the point of view from the 4 kilogram, point of view from the 8 kilogram. You could do point of view from all sorts of different ways. Suppose as the observer, I'm cruising at 3 meters per second to the right. So from the lab frame, we got this 10 meters per second and 1 meter per second. But now, as the observer, you're going to cruise along at 3 meters per second in this direction. How fast is this one going to seem like it's going?
7.
And this one?
-2.
So my momentum here would be that's 28 plus -16, which is 12. So what I'm trying to do here is I want to figure out how fast do I need to go so that my total momentum is 0. I want to figure out the reference frame in which my total momentum is 0. Well, let's run through a problem. So I'm trying to figure out what do I subtract from each of those, so I've got 4 times 10 minus whatever that speed is, plus 8 times 1 minus whatever that speed is 0. I want my total to be 0. One equation, one unknown. So I have 40 minus 4v plus 8 minus 8v is equal to 0. 48 is equal to 12v, v equals 4. So if I'm going 4 meters per second, well, in the positive direction, I just subtract positive 4, so I get 6. I get -3. 6 times 4 is 24. -3 times 8 is -24. I have a total momentum of 0. From this point of view, the 4 kilogram mass is moving at 6 meters per second this way. The 8 kilogram mass is moving at 3 meters per second this way. They are going to collide. Total momentum is 0. They will bounce. So I need to figure out what are their velocities afterwards so that I have the same kinetic energy and the same momentum. And the answer is simpler than you might think. All right, let's say the 4 kilogram mass is going at 6 meters per second to the right. Give me another velocity that the 4 kilogram mass can go so that it has the same kinetic energy.
What's the question?
Yeah.
All right, 4 kilogram mass moving to the right at 6 meters per second. Give me another, so the velocity is 6 meters per second to the right. Give me another velocity that the 4 kilogram mass can go so that it has the same kinetic energy.
Negative.
Negative 6? Yeah. Because kinetic energy is just based on speed. 6 meters per second in any direction, I'm going to get the same kinetic energy. So if they collide, and I want my total kinetic energy to stay the same and the momentum to still be 0, I can just flip the signs. So after, that 6 becomes -6. So this is my 4 kilogram mass and my 8 kilogram mass. 8 becomes 3. They have the exact same speed. I've switched the directions, but so instead of doing 24 plus -24 gets me 0, it's now going to be -24 plus +24 equals 0. So both momentums flip signs, the sum is still 0. Now I do need to put it back into my original problem frame. Well, to go from here to here, I subtracted 4, so to get out of it, I add 4. And I get 7 and -2, which is the same answers we got the last 2 times. This is what the problem would look like if I were solving this. I got my 4 kilogram mass and my 8 kilogram mass. Before, it's going 10 and 1. I have to figure out the reference frame, in which my total momentum is 0. Well, it turns out, if I solve the perfectly inelastic collision problem, so I had 48 is equal to 12 V final. This is my total momentum beforehand is equal to the total mass times final velocity. This is the PIC problem. V is equal to 4. So I'm going to subtract 4. I'm now shifting, this is the shift, to the 0 momentum frame. -6 and -3. They collide. We flip the signs. This is after. I shift back to lab frame, or the original frame of reference, by doing the opposite of what it did there, so add 4 plus 4. I find this much simpler